Okay, we are here today. Okay, so first thing today, I'm looking at setting up your quizzes and your test date for this unit. So I would like to be done 2.2 this week, have a quiz on 2.1, 2.2 on Friday, okay? And the reason for that is because next week is like a super short week. Yes, we only are here Tuesday, Wednesday, Thursday. So on Thursday, I would like to have the 2.3 quiz. Okay, there we go. And then the following week, I want to have your test. We will be done before that, okay? But I kind of like you guys to have a weekend to study. Do you know what I mean? So does that sound like a plan? Okay, so what day would we like our test? The week of the 28th. Do we have a preference? Thursday? Oh, go back. Close. Discard. Okay. Ah! Discard. Okay. Thursday? Okay, so that's Thursday, March 3rd. We may be like done before that. Like we're not going to be, yeah. So that's your Unit 2 test. So those are now on the calendar, which if you notice is at the top of the general tab. I will also be putting them over in the upcoming quizzes and tests, but I'll do that after school, okay? So there we are. Were there any questions from anything that you did for homework? That sounds like a resounding no. So shall we carry on with, I think it's 2.2D? No, yeah, D, 2.2D, which is on page 50, 50. Actually, we did page 50, we'll be doing page 51. Page 51. So last day we looked at those kinetic energy graphs and we decided which rate is affected more. Is it the rate of the exothermic direction or the rate of the endothermic direction? Endo. So let's look at this. So if we are increasing the temperature in this reaction here, which rate ends up being faster? So if we increase temperature, the reverse ends up being faster because they're both faster, but the reverse is more faster, okay? So the forward is faster, but the reverse is more faster. So which of the two is faster? So therefore the reverse is faster than the forward. So what are we making faster? Are we making products faster or reactants faster? Reactants. And if we are making reactants faster, which way are we shifting? We are shifting to the left. Excellent. So let's do a rate diagram for that. Rate goes on the Y, time goes on the X. We need to have a forward, and we need to have a reverse. What do they start out like? They start out equal, yes. And then all of a sudden here, we increase the temperature. What would that look like on this graph? What should the blue line do, the forward line? It should go up. Okay, so the forward line is going to go up. What's the reverse line going to do? It's going to go more up, more up. La 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 la. There we go. And now, what will they do? I now have my reverse rate up here, and I have my forward rate here. What will they now do? I should move that over because they're going to get hit. They will shift so the red line will go down. La 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 la. No S curves, remember, no S curves. And the blue line will go up. And remember, sometimes I like to draw that dot there because it shows when I'm transitioning from the stress to the shift, because it's not always obvious because the stress was up and the shift is also up, and when do I stop being straight up and down and when do I start curving? So okay, so that's our rate diagram. Concentration diagram. Ooh, I didn't write my reaction. N2H3, N2H2. N2 plus 3H2, la la la, 2NH3. And we are shifting that away. So in that moment, when we increase the temperature, what happens to our concentrations? They go up? They do what? They stay the same? Do they go up or do they stay the same? That's what's going to happen during the shift. But what about right in that one moment? In that moment when I increase the temperature, what happens? They stay the same. The particles are moving faster, but there aren't any more or less of them, yes? As we shift, we're going to be making more of the reactants and using up the product. But right in that moment, and I'm actually going to put like a little dot here just to show that that just is staying the same. You don't have to put these dots, but I'm just emphasizing the point that these are just staying the same in that moment, okay? So you will actually see no spikes on a concentration graph when there is a change in temperature. I think it's the only instance where you don't see any spikes. So just for temperature and just for the concentration. You'll still see them on the rate diagram, but not on the concentration diagram. And you're right, now the N2 is going to go up. The H2 is also going to go up by how much compared with the N2? 3 times. Uno, dos, tres. There we go. Okay, that didn't really look like 3 times. And if you have not successfully drawn something that looks 3 times as big, you can say that is X. And this is 3X, even though it doesn't look like 3X. Yeah? And the NH3 will go up or down? Down. 2. Okie dokie? All right. Are we ready to scroll? Okay. So, I know I had you do it last day. I'm having you do it again. To your partner, define Le Chatelier's principle. Does anyone want to commit to a definition that they would like to share with us? You guys are too scared? Yes. Stress is introduced to a system shifts to reduce that stress. Now, what's that big gap for? At equilibrium, yeah. Because if you're not at equilibrium yet and you introduce a stress, then life just gets too complicated. Yes? It's like, oh. All right, so in this little reaction here, in the forward reaction, are we releasing or absorbing heat? We are releasing heat. In the reaction bed, the forward reaction releases heat, and the reverse reaction absorbs heat. If we decrease the temperature, what has happened to the amount of heat in the system? If we decrease the temperature, the amount of heat in the system has decreased. So according to Le Chatelier, the system will then shift in the direction that, now are we going to want to release heat or absorb heat? The amount of heat was decreased. So we want to get more heat. So we want to release heat. Think of it as kinetic energy, okay? Instead of thinking of it as heat, think of it as kinetic energy, okay? So if we decrease the kinetic energy, or sorry, if we decrease the temperature, the kinetic energy in the system has decreased. So the system is going to shift in the direction that releases kinetic energy. In other words, we're turning potential energy into kinetic energy. And that's going to bring the temperature back up. Because if you have increased the kinetic energy, what are the particles doing now? They're moving faster, and if they're moving faster, the temperature is increasing. So the system, in this case, is going to shift to the, if we've decreased the temperature, here we're going to use the arrows. If I decrease the temperature, which way will we shift? To the right. Yes? So unless you're asked to explain it, you can just use the same old rule. The system will shift towards a decrease and away from an increase. Yes, and you can just treat the heat term as though it were a substance, which it isn't, but you know, you can use that, okay? So the system is going to shift to the right. So if we decrease temperature, the system wants to make it get hotter again. So it wants to make it warmer. So decreasing temperature favors the what reaction? Endo or exothermic? Exothermic reaction, since it releases heat to bring the temperature back up. Increasing temperature favors the endothermic reaction, since it absorbs heat to bring the temperature back down. Are we okay with absorbing heat, bringing the temperature down? We're turning kinetic energy into potential energy, okay? No. So let's do a rate and a concentration diagram from this when we decrease the temperature. Do you guys want to try it on your own? And then check with me? Yeah, give it a try. Does anybody want to come up and draw it? It's fun, you can choose the pen color. Anyone want to try? No? Sure? Okay, cool. And I'll lend you my glove because otherwise, like, the hand on the screen makes the screen move around. So this is my high-tech solution, or my low-tech solution to a high-tech problem, as is the fact that they put the erase button exactly where one would hold a pen. So this is my solution to that problem. I got like those little rubber, those things that you put on pencils for little kids, and I cut it so that it would like have a little hole. like you pay all these money for all these things, and the best solution I've literally found is a fingerless glove and a little foamy. You want to try? It's totally fine if you get it wrong. You know that, right? Yeah. So, there you go. And you put on the glove. There you go. Yeah, yeah. Okay. Yeah, yeah.
I really don't think I got this.
And you know what? If you didn't, this is going to be the perfect way to like solidify it in your mind that it's not that way.
Oh, what the heck? This is hard.
You get used to it over time, but yeah, it takes a little practice, right?
So, we won't. That doesn't look right.
It's shocking that I can do this at all, isn't it? All right, thank you.
Oh, no.
That's okay.
I think it might go the other way. Would it decrease or would it increase?
So the whole point of shifting is to get the rates to go back to being the same. So instead of the forward rate going up, it's going to have to go down, and instead of the reverse rate going down, it's going to have to go up. Are you ever going to forget that? Nope. Was it worth doing? Yes. Now, why did the reverse rate go down more than the forward rate? Why did the reverse rate go down more? Nobody? Because it's the endothermic, and the endothermic rate is affected more. Yes. Did anyone want to try the concentration diagram? Oh, sorry. Did anyone want to try the concentration diagram? You guys are shy? You still want to draw? Okay. What should I do to my N2? Down. Okay. Are you happy with me? No, what did I do wrong? I made an S curve. Okay, so that's no good. Okay, so let's do this properly. What should my H2 do? Go down 3 times as much. Are we happy with me? Is this a happy graph? What is wrong with the H2 curve? It's not a curve. You gotta be a curve. Okay, so here we go. All right, now NH3, down or up? Up by how much? 2, and oh, could do it in green. 1, 2. There we go. Okie dokie. Now, do we need this up here for a little bit longer, or can we continue on? We can continue on? Okay. So, explaining these shifts in terms of Le Chatelier's principle and in terms of rates. So, if we decrease the temperature was decreased, the system shifts whichever direction. Oh, this particular one would shift. Oh, I'm hearing both. Right, right. In order to release, release, one of those. Heat to bring the temperature back up. A decrease in temperature does what to both the rates? It decreases both the rates, so I'm going to cross that one out. Both the forward and reverse rates. A change in temperature affects the endothermic rate more. And then the rate of the forward, which reaction is faster than the other one? The rate of the forward is greater than the rate of the reverse. I have trouble doing that without drawing my arrows. Do you know what I mean? Like, I'm like, did I actually do that right? So what I would do is I'd be like, okay, they both decreased, but the reverse rate decreased more. So that means my reverse rate decreased more. This one decreased less. That means my forward rate is faster than my reverse rate. I would literally be drawing those arrows to think my way through it. Okay, because otherwise my poor little brain gets a little fuzzy. All right. So if the forward rate is faster than the reverse rate, then what is being made faster, products or reactants? Products. And they're being made faster than reactants. So we are shifting to the right. Okay, we now have our heat term on the reactant side, and we are increasing our temperature. So in terms of Le Chatelier, we would say we increase the temperature, therefore the system shifts right in order to absorb heat to bring the temperature back down. Huh? Oh, this is wrong here. Okay, a temperature, yeah, we need to correct that. The increase That way when I'm going through and redoing this for next year, I'll see like that great big star and mistake and I'll correct it. Okay. All right, so the increase in temperature does what to both rates? Increases both rates. And a change in temperature affects the endothermic reaction more. And so I'm going to say, okay, there's my endo is forward, so, and we're speeding them up, so that one's going to get faster, faster, and this one's only going to get faster. So the rate of the, that's why we draw our arrows. The forward rate was endothermic, so it got faster, faster, whereas the reverse rate only got faster. Yes? Yes. It doesn't matter, but you should work with whatever you're given and not like randomly switch things up because that would be okay. So in this case, the way it's given, the NH3 is the reactants. Okay, and the H2 and N2 are the products. If I wrote it the other way around, we would say it the other way. It depends on how the person presents it to you. Yes? So, because earlier I think we had it the other way around with the other ones in the products and they're, so you can write it whichever way you want, but just go with whatever's given to you in the question. Okay? So the rate of the, so if we increase the endo more, that means that the forward rate got increased more and the reverse rate got increased less. Yes? So which rate is faster? The rate of the forward is faster than the rate of the reverse. Did we follow that? Yeah? And therefore the, who's being made faster? Products are being made faster than the reactants, and therefore the system is shifting to the right. One other little thing that you will be called upon to do in a system like this is if you see a shift, you should be able to tell whether the reaction is endo or exothermic. Okay, the forward reaction or the reverse reaction. You'd have to specify. So we heat this tube and it became a darker brown. So we heated the tube and it became a darker brown, and remember the brown one was the NO2. Is the forward reaction endo or exothermic? Tell your partner what you think and why. So what do we think? Is the forward reaction endo or exothermic? It is endothermic, yes. Because when we increased the temperature, the system did shift to the right. Yes, it shifted that way. And that would be in order to absorb heat, to bring the temperature back down. And if you want to do, you could be like, oh, if I put my heat term here, then if I have this going up, then that's going to go shift away from that increase. Yes? That's another way to do it. So just writing in your heat term. Therefore, the heat term must be in the reactants, which means the forward reaction is endothermic. Oh, exercises, good. Okay, moving on to 2.2e. These are the things that are not stresses, so basically you don't have to worry about them very much. So this is on page 57. Things that are not stresses. Catalysts are not stresses. What does a catalyst do? It increases the rate. How does it do that? It provides an alternate pathway. So on an AP exam, you don't want to just say that it decreases the activation energy. You want to say it provides an alternate pathway with a lower activation energy. Like I've read the readers' reports. The readers are the people, they don't call them markers, they call them readers. And if you read their comments, they don't want to hear just the one, they want to hear both. Okay? So the catalyst provides an alternate pathway with a lower activation energy, and that would be like what you would just normally say. And because we're looking at shifting, this actually happens for both the forward and the reverse. And as it turns out, both rates speed up the same amount. Okay, so both rates are still equal, so therefore there is no shift. So, rate diagram. Forward, reverse, forward, reverse, add a catalyst, what happens to our forward rate? Increases. Yay. What happens to our reverse rate? By how much? Same. So remember, when we had something where they were different, they were trying to get back together at the same rate, but they are already at the same rate. So what do they do at this point? They just stay flat, yeah? At the new, faster rate. Concentrations. Here's A. Here's B. And we are going to add a catalyst. What happens? Nothing. Super boring graph. Yes? Now, The one thing that does happen is if you start out and you are not already at equilibrium and you just say put reactants in or something, you will get to equilibrium faster. Yes? But if you're already at equilibrium, it has no effect. Okay? So if you start with only reactants or products, it does make the system reach equilibrium faster if you started with only one or the other. So let's say we started with reactants only. Yes. Like this one? Yeah, we're starting with reactants only. Yes. So we're going to look at what happens. So this is with a catalyst and then without a catalyst. We'll actually draw them on the same graph, okay? So what is my forward rate going to be like? And what's my reverse rate going to be like if I have only reactants? Forward rate will be, if we're starting with reactants, what can you say about the forward rate? Is it fast? Is it slow? Is it zero? Fast. We're starting with only reactants. Reverse rate. Is it fast? Is it slow? Is it zero? Zero. Now, what are those two rates going to do as equilibrium is approached? They're going to come together. And here we go. There we go. This is what it would look like uncatalyzed. How would that curve change? How would those two curves change if we catalyzed the reaction? They would just be steeper and we would reach equilibrium sooner, yes? So yes, pardon me. I don't think you're ever going to have to draw this graph. I think that is highly unlikely, but does it kind of make sense to you that you just get there quicker? Okay. Concentration diagram. Reactants and products, we got what, A in equilibrium with B? Oh, hang on. So if we started with reactants only, where should A be? High. And if we start with reactants only, where should B be? Low. Low or zero? Now, where they end up, it doesn't really matter. You can have A higher than B, you can have B higher than A, we don't know unless we know the position of the equilibrium, but I'm just gonna make them go here because this is not so complicated. La 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 la. There we go. La, 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 la. Okay. And what would happen to that if we catalyzed it? It would curve faster. And that's it. And because my drawings are kind of crap, on the next page, there's actually pretty drawings that somebody did like professionally, and I stole the images. Yes? Oh, look how pretty. Yes? So that's nicer than my drawing. Yeah? Anyway, there we go. Okay. Yep. Okay. Okay, so here's some concentration diagrams where we're starting with reactants only. What can you say about the equilibrium position of reaction A compared with reaction B? What can you say about the equilibrium position? In situation A, what is favored at equilibrium? The products are favored at equilibrium because we have more of them, okay? Do the colors look different on your thing? Okay, I'm gonna have to work on that. I'm gonna have to go in and put in some dashed lines or something like that. Okay, so this is our products here. This is our reactants here. So the products are favored at equilibrium. And what that means is that the concentration of the products is greater than the concentration of the reactants. Yes? If that's the case, what could you say about the KEQ value? What does KEQ equal? It's the ratio of the molarity, but what goes on the top? Products over the reactants. And if the products are greater than the reactants, what can you say about KEQ? KEQ is greater than 1, okay? And I'm not sure why I wrote this like so it's over at the other diagram. I'm gonna move it back over here. Here we go. Products is greater than reactants. And I don't know why I have this arrow. That looks confusing. I'm just gonna get rid of that. Okay. In this other situation, here's our reactants. Here's our products. What's favored at equilibrium? Reactants are favored at equilibrium. Which means that the concentration of products is lower than the concentration of the reactants. And what does that tell us then about our KEQ? It's going to be, which is the products over the reactants, of course, it's going to be less than 1. So I think this was just reviewing the language around this, and I threw in the little KEQ bit. So in diagram A, the position of the equilibrium sits more towards the reactants, so we say that it favors the reactants. Huh? Oh, products, and that's what I meant. Products. And then obviously for diagram B, it's going to be it sits more towards the reactants. So they favor the reactants. All right, an inert gas. Inert means unreactive. Adding an inert gas, an unreactive gas. For example, which gases are always unreactive? Noble gases. There are other ones that won't react in certain circumstances, but you're guaranteed a noble gas won't react. Does it affect the concentration of the reactant particles? No, it does not. Does not affect the concentration of the reactant molecules. And if you have not affected the concentration of the reactant molecules, have you changed the rate? No. Therefore, the forward and reverse rates are not affected. Therefore, adding an inert gas causes how much of a shift? No shift. Sometimes people are like, but aren't there more particles? Wouldn't just everybody collide more, or it would block the particles from getting at each other? The thing to remember about gases is although we often show them like this, it's really like there's one here, and there's one there, and there's one here, and there's one there. The space between them, like if they were big enough that I could like hold them, would be like this. They'd be so far away from each other. So they're not really blocking each other or causing them to collide, or at least if they do block from hitting just as often, the rebound will cause them to collide. So the easiest thing to remember is that an inert gas does not affect it because it's not changing the concentrations. Okay? Don't get all wound up in, oh my gosh, they're blocking the collision. No, there's no blocking. There's no extra collisions. Just doesn't affect the concentrations, doesn't affect the position. Okay, so rate diagram for an inert gas. Concentration diagram for an inert gas. These are so exciting. What do you think is going to happen here? Absolutely nothing. Right? Here, we add an inert gas. Woo! The rates do not change. Here, we add an inert gas, and what happens? Nothing. Super fun, yes? Now, changing the amount of a solid or liquid. What do you know about solids and liquids and their presence or absence in the KEQ expression? They don't make a difference because can you change the concentration of a solid? No, you cannot. Okay? Solids and liquids are pure substances and therefore they do not have concentrations. You can only have a concentration if you have a solution of something, which is a homogeneous mixture. of something, okay? So here is a solubility equilibrium. So ionic crystals, when you dissolve them in water, they break apart, okay? And if we keep adding more solid, okay, so if we add more solid in, eventually we'll get to the point where we have a saturated solution. It's full of as much solute as possible. This is going to be unit 3, by the way, this stuff, solubility equilibrium. And what will happen is that for every, these are labeled M and X, for every M and X that dissolve, yes, an M and X will also reprecipitate. Does that make sense? Sort of. And if it doesn't, that's okay. That's a whole nother unit. Okay? No. Maybe I drew it better down here. I did. Okay. So for every one metal, non-metal, MX that dissolves, another dissolved M plus and X minus, it will recrystallize into the solid. Is that part okay? Every time one particle dissolves, another one recrystallizes? Yeah? Okay. So we have a system then that is at equilibrium. If we add more solid, we are able to dissolve more often. But there is also more surface for recrystallizing. Yes? So up here, there's not as many particles available to dissolve, but there's also not as much surface for it to recrystallize on. So both rates are slower if there is less solid present, if there's less surface area. Both rates are faster if there is more surface area. But it doesn't affect the position of the equilibrium at all because it speeds up both the dissolving and the precipitating. And if you don't feel awesome about that yet, like I said, that's a whole nother unit and we will be going over it in more depth as we get there. Okay, but this is a nice little intro to it. Okay, that's it for that one. You should be able to do quick fire practice. Yes? So making quick predictions. Le Chatelier's principle says that the system shifts in which direction in response to an increase? It shifts away from an increase, and it shifts towards a decrease. So if you have a concentration increase, it's going to shift away from that increase. And if you have a concentration decrease, it's going to shift towards that decrease. And then the only one that's sort of the lone one out, the odd one out, is volume. And if you expand the volume, you will shift to the side with more or fewer gas molecules. More molecules fill up the space. If you squish it, you will shift to the side with less gas molecules because there's not enough space, okay? So those are just quickly predicting things. And then there is predicting the shift, pages and pages of it. Just, can you do it quickly? Yes. So you can decide how much of that you're going to do. Maybe you choose to do like every other problem. Do you know what I mean? Like you don't necessarily want to do all of these. So for homework, because I don't want to get into anything more today, and we've got so much that we could assign you, and I don't see you till Thursday. How about I assign you all of, no, I'm kidding. Oh, no, okay. Let's do something reasonable. Let's do the temperature one, 2.2D. How big is that? Let's see. It's moderate. Yeah. Okay. So 2.2D, do that one. And then how about 2.2G? Just do 1 and 2. Yeah? Now, your quiz on Friday will be on all of 2.2. So if you have a little extra time and you're like, ooh, I might like some practice on some rate diagrams, that would be 2.2H. Yes? If you think, oh, I would like some practice on Le Chatelier's principle and concentration diagrams, that would be 2.2I. Okay, so this is all on the quiz on Friday. Yes. The homework is 2.2D and 2.2, was it G? G, numbers 1 and 2. But like I said, if you want to work ahead, because you've got a couple of days, you could do some of the other stuff. There's like extra practice. Don't do the extra practice before the quiz. That's like if you take the quiz and you're like, oh, I didn't do so hot on the rate diagrams, then you can do the extra practice. But don't go home and drive yourself crazy trying to do every problem in this book before Friday. Yes? There's a lot in here. If you just do every second question, that might be a good way of doing it, or pick every third question, whatever gets you to the point where you feel good about section 2.1 and 2.2 on Friday. So that would include characteristics of an equilibrium. Yes? Do we remember what those are? The system has to be closed. The temperature has to be constant. The forward rate and the reverse rate are the same. The macroscopic properties are not changing. What are macroscopic properties? Observable properties. What have I missed? It can be approached from either direction, which I always find like a little bit silly, but you know, it can be. You can start with products and end up at equilibrium. You can start with reactants and end up at equilibrium. Reactants and products must be present, both of them, yes. Okay. So, et voila. We're done a little early, so if you want to work on some stuff, you can work on some stuff. Yes. Yeah. Yeah. Okay.
Like this square.
This one here.
Yeah.
Okay. So if we decrease the temperature, okay, do you want a fire or do you want like one of those thermal packs that you break and it goes cold? Which one do you want? If we made it colder, would you want a fire?
A thermal pack.
You want it to get colder when it's colder?
I guess a fire would be more.
Okay, so the thermal pack is like not like the one that heats up, but the one where, you know, if you like squish it, it goes cold, and so you can put it on an injury.
Oh.
Do you know what I mean?
Oh, I thought you mean like the.
Oh yeah, not the one that gets hot. The other way around, because
Okay.
they have them in like first aid kits, you know. So if you injured yourself, you can squish the little thing and it gets cold.
Oh, okay.
Okay. Do you want that or do you want the fire?
A fire.
You want a fire.
Yeah.
Fires are exothermic because they
release
heat and they bring the temperature back up. Okay. Does this part make sense?
Yeah.
Okay. This is usually the one that messes people up a little bit. Okay. Yes? So you can always just be like, oh, endo is the opposite of exo. So just think through the endo one or the exo one and then do the exact opposite for endo.
Okay.
However, let's talk about this one. So if we increase the temperature, kinetic energy has gotten greater. So we want to take the system is going to take some of that kinetic energy and it's going to transform it into potential energy. Yes? So we're going take some transform it into potential energy. So that means our potential energy diagram would be going up. So this is endo, yes. And so we have absorbed heat. The potential energy went up, but the kinetic energy went down, which brings the temperature back down.
Okay.
Yeah?
Okay.
Yeah.
That makes sense.
Yeah.
So when you're adding like a change to like a stress to the, let's say on the diagram, like, so for this one we decrease the energy, right?
Yes.
So
I can look upside down, it's all good.
Oh, okay.
I'm a teacher, it's what we do. I've been doing it for 30 years, so you know, yeah, okay.
So in this one,
Yeah.
you decrease energy.
Uh-huh.
So in this situation, the reverse is more impacted on the decrease.
Yes.
Okay. So the decrease is, I mean, the reverse is an endothermic reaction.
Yes.
So that's the part like I don't understand, because like when you have like a stress, like and it favors the endothermic reaction, right? And that stress is decreasing it. And I look at this and I was like, increasing the temperature favors the endothermic reaction. And I was like, well, it kind of favored the endothermic reaction on the decrease. You get what I'm saying?
Yeah.
So like, is that only for this? This only refers to the shifts back, right?
Increasing temperature favors the endothermic reaction. So, okay, you're gonna have to repeat your question again because I got lost in there somewhere. Okay.
So like this point here, right?
Yes.
That's the shift or the stress. Right?
Stress, yes. So we decrease temperature.
Yeah. So
yes.
we decrease the temperature.
Uh-huh.
In this situation, why is like the okay, yeah, so you decrease that, which means that it's like a it's forward reaction. So that's why the
exothermic is favored. Yes.
Okay.
Yes.
That makes sense.
Yeah.
Okay, and then the shift.
Yeah.
That's when we look at this box.
Yeah. Yeah. So now it's gonna come. So now we're releasing heat. So now it's gonna come back up.
Okay.
Yeah.
Oh, okay.
Yeah.
Okay.
Okay. Cool.
That's all.
Yeah. You know what? Honestly, the arrows they'll help you out all over the place. Yeah.
Okay.
Yeah.
Okay. Thank you.
Cool. Anyone else have questions about anything? Yeah. Next. Yeah. What does it naturally tend towards? It naturally tends towards more randomness, yes? I have to work to make that best. I agree. So entropy, you're going to be looking at saying which side has more sort of randomness, particles kind of reacting more random. If you've got gases, instead of solids, that's more random. Once you go to more random side. Homework. Let's post that up. Oh, I can stop recording.